I'm Pat Dugas. Welcome to a screencast on inverse functions and relations. We're going to look at inverses. We're going to look at when an inverse function exists and how to determine if two functions are inverses of each other. And we're also going to be able to determine how to find the inverse of a function if it does exist. An inverse occurs between two relations if and only if the set of ordered pairs of the first relation, let's call it A, is reversed in B. Let's see an example of what I mean here. So let's say A is a relation which has three sets of ordered pairs in it, 2, 4, 3, 7, and 4, 12. For B to be an inverse, I'm going to take those ordered pairs in A. 2, 4 becomes 4, 2. 3, 7 becomes 7, 3, and 4, 12 becomes 12, 4. As you might expect, graphically, inverse relations, since they're switching in the x and the y coordinates, they're reflected across the line y equals x. Let's look at an example. We're given the ordered pairs of the relation A is 1, 3, 6, 3, 6, 0, 1, 0, and those happen to be the coordinates of the vertices of a rectangle. So we want to find the inverse of relation A, and we'll describe the graph of it. Now, some symbology here. If I have a relation or a function A, its inverse is known as A minus 1. So that's not an exponent, that's just the inverse notation. That is not A being raised to the negative 1 power, that's an inverse of A. So to find A inverse, the inverse relation, we're going to reverse the coordinates of the ordered pairs in A, which is green. So 1, 3 becomes 3, 1 in the inverse. 6, 3 becomes 3, 6. 6, 0 becomes 0, 6. And 1, 0 becomes 0, 1. When we plot both of those on an XY coordinate axis, the green points look like this. Your 1, 3, your 6, 3, your 6, 0, and your 1, 0. And then when you plot your blue inverse, it looks just like this. And what's interesting about that is the green rectangle of A and the blue rectangle of A inverse are reflections of each other about this line y equals x, which is also known as the identity function for linear functions. And what do I mean by the reflections? Okay, so let's take this point right here, which is on A, it's called 6, 3. Well, if I go an equal distance across perpendicular to the y equals x line, I get to its kind of sister point here, 3, 6 on the inverse. And the same is true as with all the other points. Well, why does this work? Well, it's because the x coordinate of the original relation becomes the y coordinate of the inverse, and the y coordinate of the original relation becomes the x coordinate of the inverse. So that's why this important graphical idea that relations and also functions are reflections about the line y equals x occurs. So now let's go to inverse functions, and I'm going to take my daughter's favorite food, chicken nuggets, and turn it into a math situation. So let's say, and no chickens were harmed in the filming of this, let's just say we have a process, a function that takes chickens and turns them into chicken nuggets. And we'll call that f of x. Okay, well, f inverse of x would be taking the chicken nuggets from the original function, taking the chicken nuggets as input, and turning them back into the original chickens, if that were possible. So that kind of illustrates, if you will, inverse functions. So a function's inverse, and this is red, f inverse of x, is found by swapping the domain, the set of inputs, and the range of the original function. Just like we switch the x and y coordinates in the relations, we do the same thing with the entire set of inputs and outputs in functions. And just like relations, a function and its inverse will be reflections about the line y equals x, that identity line. Now, the last thing, to be able to graphically look at a function to see if it can have an inverse, if a function passes what's called the horizontal line test, then it has an inverse function, f inverse of x. You will recall from earlier screencasts that we can tell graphically if something is a function if it passes the vertical line test. In other words, a vertical line only hits one point on the function. Well, to determine if something's already determined to be a function, to be able to find it has an inverse, we do the horizontal line test. Let's take a look at an example and non-example. So this red function here, which is some variant of the cubic function, passes the horizontal line test. In fact, it never hits more than 1 point horizontally. It looks like it does here, but it's only hitting 1 point everywhere. Therefore, this red function has an inverse. The blue function, however, if I run the horizontal line test through just about anywhere except the vertex, I'm hitting 2 points. Fails the horizontal line test, therefore this function, which is y equals x squared, does not have an inverse. Now, it's more of an advanced idea, but if we restrict the domain of some functions, we can create inverse functions. For example, if we just looked at the x squared function from 0 to infinity, we just looked at this part, then it would pass the horizontal line test. So a restricted version of x squared would have an inverse. So let's get down to it and find an inverse. So if I've got a function f of x equals negative 1/2 x plus 1, and when I find its inverse, we're going to follow a process. And the basic process is we're just switching out the x's, the inputs and the outputs, the domain and the range. So we're going to replace f of x with y just so we can turn it into a coordinate system. So the original function becomes y equals negative 1/2 x plus 1. Now we're going to swap out the x and the y. And that's what inverses do. They interchange or swap out the x and y coordinates. So when we do that, we create this equation, x equals negative 1/2 y plus 1. Well, now we've got to solve it for y, and y will become the inverse. So to get y by itself, the first thing we want to do is subtract 1 from both sides. Okay, and that's going to give us x minus 1 equals negative 1/2 y. And then we're going to multiply both sides by the reciprocal of negative 1/2, which is negative 2. Okay, and that's going to give us negative 2x plus 2 after we distribute equals y. So y equals negative 2x plus 2. Now we need to turn that into the inverse function itself. Bit of a technicality there, but in the end we get f inverse of x equals negative 2x plus 2. So the inverse of this linear function, negative 1/2 x plus 1, is f inverse of x is negative 2x plus 2. Let's look at that graphically just to make sure we got it right. So we're going to graph both the function and its inverse. And in fact, the function itself is this blue line, negative 1/2 x plus 1. The inverse line is negative 2x plus 2. That's this green line. Now, how do we look at that and determine their inverses? Well, this dashed line is y equals x, our identity. And you can see that they are reflections of each other. So if I just pick any point on the original function, let's just say 2, 0, and I look over across the line of y equals x, I'm going to see its inverse point, 0, 2, where all the points on the blue line are mapped over, reflected over the line y equals x to the green line. So graphically, we know that's right. Analytically verifying functions are inverse. Two functions, f and g, are inverse functions if and only if both of their compositions are the identity function. So if the result of f of g of x is equal to x and g of f of x is equal to x, then we know analytically that they are inverses. So verifying two functions are inverses. Let's look at f of x equals 3/4 x minus 6 and g of x equals 4/3 x plus 8. And let's say that's the answer you got for the inverse. So we want to verify it. We're going to look first at f of g of x. Okay, so that means g becomes the input into f, if you recall from the compositions of function screencast, f of 4/3 x plus 8. So everywhere we see an x in f of x equals 3/4 x minus 6, we're going to put in 4/3 x plus 8. And so this is the input for x. And so we get 3/4 times 4/3 x plus 8 minus 6. When we distribute that 3/4 to these two terms, these two cancel out, and I'm left with 3/4 times 8, which is 6, plus 6 minus 6, I just get x. Similarly, g of f of x, now f of x becomes the input into g of x, And so we get g of 3/4 x minus 6. So everywhere I see an x in g of x, I'm going to put in 3/4 x minus 6. So I get 4/3 times 3/4 x minus 6 plus 8. And when I do the same distribution, I'm going to get x minus 8 plus 8. The 8's cancel out, and I get x. So therefore, bada bing, g of x and f of x are inverses of each other. This screencast has been about the basics of inverse functions and relations, determining whether they are inverses, when inverses occur, and how to actually find an inverse of a function if it does exist.